Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 57, and it is entitled The Nature of Light, Huygens Principle, Interference, and Young's Double Slit Experiment. Here we begin to bump up into some really modern physics. This lesson is in 3 sections. All of them are very intricately related to each other, and we'll take them one by one. The first section is entitled The Nature of Light. So far in this course, we've been talking about how light behaves, dealing with optics. We've dealt with mirrors, we've talked about lenses, and we have done geometrical constructions to be able to describe images produced by optical systems. But we haven't really talked about what light is. This is a philosophical question, one that has been debated for many years, and it hasn't been until the last couple of centuries that there is evidence that supports one side or another. Since long time ago, people have debated what is light, the stuff that stimulates our sensation of sight. And there have basically been 2 camps of thought. There's the particle theory and the wave theory. In the particle theory, the idea is that light is a stream of particles that somehow stimulates the eye, and those particles interact with matter, and the kinds of things that we see light doing is a result of particle behavior. Adherents to this include some Greek philosophers and even Sir Isaac Newton. These folks basically said that we can describe the behavior of light, modeling it as if it is a set of discrete bundles that interact with matter, and we can describe reflection and refraction based on these little bits, these little bundles, these little balls of light. On the other hand, the wave theory was supported by other Greeks and a contemporary of Newton whose name was Christian Huygens. This school of thought said that light behaves as if it is some sort of wave, and the things that we see light do when it interacts with matter, reflection and refraction, can be described in terms of wave principles. In a moment we're going to discuss Huygens' way of modeling how it is that light propagates. Both the particle theory and the wave theory had people who were proposing it, but they really had no evidence about whether light was a particle or whether light was a wave. These people who were arguing about the nature of light, particle or wave, basically were expressing their opinions. Until evidence came in, then neither theory really was stronger than the other. Until 1803, Thomas Young and something called Young's Double Slit Experiment. And we'll have much more to say about that in just a moment. What we are going to see is that Young was able to demonstrate if light could be shown to experience interference, then it must be that light shows wave properties. Light must be behaving as a wave. Particles don't interfere with each other. Waves do. So if light shows interference phenomenon, then it must be a wave. And in fact, this was a breakthrough, so that about 20 years later, nearly everyone in the physics community tended to accept the wave theory of light. Towards the end of the 1800s, there were a set of experiments that were done that were called the photoelectric effect that were not explainable using the wave theory of light. In the photoelectric effect, what happens is light shines on a freshly polished piece of metal, and electrons are ejected from the metal. And the measurements that scientists were making, they were not able to explain using a wave model of light. So in 1905, a young German scientist working in a Swiss patent office, whose name is Albert Einstein, came up with a theory which explained this. This is called the photoelectric effect, the photon theory of light. Einstein, in 1905, wrote 5 papers that basically set him into the world stage as a brilliant scientist. And it's for this 1905 paper, in his explanation of the photoelectric effect, that he won the Nobel Prize later on in his life. In this paper, what he did was he explained the photoelectric effect in terms of modeling light as if it were a particle. So all of these proponents of the wave theory now had to take a step back and say, we can't explain this physical phenomenon with our wave theory, but Einstein can explain it with a particle theory. And so now we have the particle-wave debate going on once again. So what does that mean about light? Is it a wave? Is it a particle? Well, it depends on the experiment that you do. And Niels Bohr, in the early 1900s, this is probably the 20s or the early 30s, actually came up with something called his principle of complementarity. For our purposes, what this says is that the kind of effect that you see, the kind of nature that light reveals when you do an experiment, depends on what the experiment is. And it's not possible to say that light is a wave or light is a particle, but rather light has a dual nature. And that's about where things stand to this day. Is light a wave? Well, if you do an experiment that looks for wave properties, then yes, you can find evidence that light is a wave. Is light a particle? Well, if you do other experiments looking for the particle effect, then it's possible to model light as a particle. But it's not possible to say light is a wave or light is a particle. It depends on the experiment that you do. In general, we find that the higher the frequency of the light is, it seems that the particle nature of light tends to predominate, whereas the lower the frequency of the light, then the wave nature tends to dominate. And where that cutoff is not very clear. It turns out that the photoelectric effect can be seen for frequencies of light that are in the visible range. So if you want to press me for a frequency of light that's a cutoff frequency, then we would say, well, about the visible range, that things that are lower frequency than visible light tend to be waves, whereas things that are higher frequency light than visible tend to behave as particles. However, it is possible to show higher frequency light behaving as waves, and we will talk about those things when we talk about diffraction. We're going to study the photoelectric effect in a future lesson. We're going to study Young's double slit experiment in this lesson, but you ought to be aware that light has this dual nature, and there will be questions on the AP exam about the nature of light. For the rest of this lesson, we're going to focus on the wave nature of light, and that's how we're going to model it for the effects that we see in the rest of this lesson. We're going to begin with something called Huygens principle, and then we're going to move on to Young's double slit experiment. Suppose for a moment that we have a wave that's incident onto a boundary that separates two different materials, say like a piece of glass that's in air. We know from our everyday experiences that some of that incident wave is going to be diverted back as a reflected wave, whereas the rest of it is going to be transmitted across the boundary or refracted. We have written phenomenological equations called the law of reflection and the law of refraction, or Snell's law, in terms of things like index of refraction, and we've measured these angles and we've come up with these equations, but we've not ever had to decide what is the nature of the ray that is incident onto this boundary. On a microscopic scale, we could actually envision an assembly of atoms that scatter the incident wave, the incident ray. The manner in which these emitted light wavelets superimpose and combine with each other will depend on the spatial distribution of the scattering atoms. What that means is that you can look at this interface between the air and glass as being made up of atoms of a different kind of material. And these atoms are going to scatter this incident ray both back into the air and to transmit it through the glass. How can we determine what the new form of the waves are going to be? A preliminary step towards the solution to this problem was given by Christian Huygens, a Dutch physicist who is a contemporary of Newton. This has come to be known as Huygens' principle. Here's what it says. What Huygens says is that every point on a primary wavefront, the primary wavefront being the place where the boundary is, serves as the source of a spherical secondary wavelet such that the primary wavefront at some later time is the envelope of these wavelets. These wavelets will advance with a speed and a frequency equal to those of the primary wave at each point in space. If I want to know what the wave at some later time is going to be, then I construct myself a wavefront with spherical sources. I let those sources produce a wave, and then I find the envelope of that wavefront at some later time. I have a simulation that I would like to show you to illustrate this. In this simulation, we're going to look at reflection and refraction using the principle of Huygens. So I'm going to read the text that's in this white box here and demonstrate it using these two different materials. The yellow material has a low index of refraction. The blue material has a higher index of refraction. The plane wavefront runs diagonally against the boundary of two different media. The wave has a different velocity in each media. So you see coming down here from the top left a wave that's going to be incident onto this boundary. And we're going to follow what happens to this wave as it strikes the boundary. Part of it's going to be reflected, part of it's going to be refracted. Now if you look here at this interface between medium 1 and medium 2, there are a whole bunch of points there. Those are going to serve as the source of wavelets as this incident wave hits it. Upon arrival of the wavefront, points along the boundary behave according to Huygens' principle. Each point can be regarded as a spherical source of light. So now we're going to let this incident wave hit them, and you'll see that when it hits each source, each of those points, that a spherical wave that is blue that has a higher velocity is produced, and a refracted wave that has a slower wave velocity that's in red is produced in the second medium. And what I want you to see is that the envelope of the blue wave there is going to be the wave front of the reflected wave that travels up and to the right, whereas the envelope of these red waves down here traveling downward and to the right is going to be the refracted wave. The superposition of all elementary waves results in a new plane wave. Note that the direction of the propagation of the plane wave changes when moving from medium 1 to medium 2. In this case, the angle of incidence is 45 degrees. We get an angle of reflection of 45 degrees, and the angle of refraction, or the angle of transmission, is 20.7 degrees. That's assuming that we have an index of refraction in the yellow material of 1 and an index of refraction in the blue material of 2. The direction of propagation of the wave is now drawn. It is the line perpendicular to the wavefront. So what you see is the refracted wave is given by this red arrow that's down below in the blue. The reflected wave is given by the blue arrow that's to the upper right. A wavefront rarely comes alone. So here we're showing several waves coming together, several wavefronts incident on this boundary. And so these atoms, these sources of secondary wavelets, are producing several different waves at the same time. I'm going to pause it for just a moment so that you can see the wavefront 1, 2, 3, 4, 5, 6, 7 on the reflected side, and then below the refracted side 1, 2, 3, 4, 5, 6, 7, 8 almost different wavefronts that are there.